Good morning, friends. Today we'll cover this three topics here. Is Initially we will try to understand regarding the resources of AWGN channel here. Okay. Uh, Within that one, we try to understand regarding continuous time AWGN channel here. Then the power and the bandwidth here, right? So these two topics we will discuss here. Okay, so initially, like resources of AWGN channel here. Okay, so let us consider that we have a channel here whose bandwidth is W. Okay, so we have considered the AWGN channel here. I think you know the meaning of this AWGN here. So AWGN is nothing but here. It's an additive white Gaussian noise here. Okay, so where noise is being added to the signal here. Okay. Whenever transmitted signal is transmitted from the transmitter here. Okay, so while traveling through the particular channel, there is addition of a noise here. Okay, so when that same signal is been received at the receiver here, so received signal is equivalent to whatever the transmitted signal plus there is some noise here. Okay, so that's why we it is represented as a additive here. Okay, so what is the meaning of this white here? Okay, white usually refers that whatever the noise components we are having here, okay, all are having the same power distribution here. The meaning of white is the noise component is having the same power distribution at every frequency level here. Okay, so and remember white noise has a constant power spectral density across all frequencies here. Okay, now white is taken into consideration as a Gaussian here. Okay. So usually noise represents random nature here. Okay. So whatever the source is there, noise is there, noise source is there. Okay. Usually it will be having a random nature here. We don't know this particular at this particular time this much noise is coming or not. Okay. We may have less noise, we may have more noise here. Okay. So whenever we try to have the mathematical model for this particular noise here, that could be calculated with the help of a probability events here. Okay, so in that one, when we have the mathematical model for this noise source, which is random in nature, we'll have a Gaussian distribution here. Okay, that's why we have taken it as a Gaussian noise here. Okay, so I think people came to know regarding the additive white Gaussian noise here, right? So in this context here, today we try to understand from the point of the bandwidth and from the point of the power constraint here. Okay, power is measured in watts here, bandwidth is measured in uh, hertz here, right? Okay, so it has been represented by W here and power by P here. Okay, now there is also spectral density that has been defined for this continuous time AWG channel here, that is N naught by 2 here. Okay, so let us understand here. As you can see in this PPT here, you have a power constraint here. We may be having power. I think you know the definition of power is signal square. It is that, right? So as a signal is nothing but here you're having x of n as a signal here. Okay, and if at all you wanted to calculate the power is nothing but square of the particular signal will give us the power or energy you can consider here. Okay, that's a summation of n is equal to 1 to capital N Sn whole square is that. It should be less than what here, the number of whatever the signals into the total power constant here, that is NP here. Okay, you can see here this x of n is given as an input here. There is always an additive noise here, that is z of n here, which is having a normal distribution you can consider here, zero mean and variance in n naught into w here. Okay, so y of n is equal to x of n plus z of n here. Okay, you know y of n is nothing but your output here and x of n is the input plus whatever the noise that has been added while traveling from one place to another place or from transmitter to the receiver side here. Okay, right? So here again, usually noise is independent here. Okay, it is in the quadrature components or in phase components here. Okay, so uh, complex channel, or you can say that one complex symbol can be a combination of what you can say that two real symbols here. Okay. So that's what has been written here. One complex symbol is equal to two real symbols here. Okay. So now in this case here, how exactly our capacity equation could be written here. Okay. So here you can see uh, two real symbols we have considered, right? 2 into 1 by 2 log of 1 plus of power divided by 2 and not into w divided by 2 here. This bits per symbol time here. Note, we have to note one point here is what about the signal to noise ratio here? Okay, signal to noise ratio is given by p divided by n naught into w here. Okay, this is nothing but here. This is a signal to noise ratio per complex symbol here. Remember, okay, per complex symbol, if at all we try to find out the signal to noise ratio, okay, is nothing but here, that is p divided by n into n naught into w here. Okay, so if at all we consider that we are having a W complex samples per second here. How many samples per second? W, capital W represents the, here in this case, W samples. If you consider here, what about the capacity of the continuous time AWGN channel here? That has been multiplied here, W into what you can say that log of whatever the P divided by N naught into W plus 1 is there. Okay, bits per second here. But this could also be written further. Here it is, that is log of 1 plus signal to noise ratio bits per seconds per hertz here. Okay, SNR is nothing but here, you know, that is P divided by N naught into W here. Okay, that is nothing but here your signal to noise ratio here. Okay, right. So this is how we can write the capacity of the AWGN channel here, considering P as a power constraint here and W as a bandwidth in hertz here, right? Okay, right. This is how we can understand regarding the continuous time AWGN channel here.